Hey, it's Mr. Kane here again, and this talks about waves. Now, a long time ago, my dad said to me there's just three kinds of waves. There's the long wave, the short wave, and the microwave. But hopefully by the end of this, we'll all know better. So, what exactly is a wave? They tell us a disturbance or vibration that propagates through. There's lots of big words here. What does that all mean? A disturbance or vibration, a shaking, a moving that propagates, that travels, that moves, that takes a journey through a material medium, a something. So a material, something made out of stuff or space that is anything. It's empty space, a vacuum. So a wave, a vibration, a wiggling of something that travels or propagates through a material medium, stuff, or space, or nothing. So, here we go, there's a wave. The wave you see at the beach, surfing, riding on that. There's a wave that guys are shaking into a rope, so it's a vibration, you can see that, travelling through the rope. The rope's the medium. There's light waves. They travel through space from the sun to us. Nothing in space, but the light travels through it, propagates. A heat wave. Heat is a kind of a radiation. It can travel through space. It can be conducted through stuff as well. So it's travelling through things. It's a wave as well. So there's some kinds of waves. So what types of waves do we have? Mechanical waves. Think about mechanical. Think about that word. There's a clue there. So like all waves, they need energy, and they create this disturbance or vibration in an elastic medium. It's the stuff that can move. So, the water, it can move, it can slosh about, we can put energy into it and get a wave out of it. And the surfer's using that energy to ride the wave. I tried surfing. I was very good at just getting wet, but it was a lot of fun out in the sea. And these guys here are putting energy into the rope, an elastic medium, and wiggling the rope backwards and forwards, and you can see the energy making the rope move up and down. Now I work here in Christchurch, New Zealand, and in the past years we've had some quite large earthquakes here, both here in Christchurch and close by, and earthquakes put energy into the ground, and enough energy, it is an elastic medium, and you can see it wiggling like that rope. Well, I haven't seen it wiggle quite that much, but I've seen it wiggle, and it is very loud and not something to, I'm glad they're finished. I'm not looking forward to any more in the future. So what types? Again, mechanical, and the other one is electromagnetic. You may have met that term somewhere before, maybe not. So it can travel through nothing. This is stuff that can travel through space. So we've got the light waves travelling through space, through the air. They don't need anything. Heat waves are electromagnetic waves. Other electromagnetic waves that you may be familiar with are the radio waves that you might listen to. The signal from your TV that you watch is often carried by electromagnetic waves. And if you've got a cell phone handy, it's also using them. And these waves are fast. They travel at 300,000 kilometres a second. The speed of light. And they come in a couple of different forms. There's the longitudinal wave and the transverse wave. So longitudinal wave, it's moving along the medium. So if we're looking at the spring over here, here is a pulse in the spring, and this is the direction it's moving. There's another pulse in the spring. So it's moving along the direction of the spring. Whereas a transverse wave, you can see the wiggling up and down. So it's moving up and down, but the wave itself is travelling along this way. So a longitudinal wave travels in the same direction as the energy, whereas a transverse wave, it moves up and down at 90 degrees to the direction of the energy moving. And the energy is moving, but not the stuff. The stuff moves a little bit, like the longitudinal wave, the little compressions there, and the transverse wave, the wiggling up and down, but there's no bulk transport of stuff from one place to another, just the energy moving. So what things do waves have that we need to know about and measure? We measure amplitude. Anyone heard of AM radio? That's from amplitude modulation. And there's the amplitude there. It's measuring simply the height of the wave. So here's the wave peak or crest. There's the center line, and that there is your amplitude. We can measure it down to the troughs of the wave as well. Bit trickier to see in a longitudinal wave, but the amplitude is sort of the distance from one side of the compression zone to the other. Wavelength. So there we go, wavelength, that's the distance from one crest to the next crest, or from one trough to the next trough. That is the wavelength. There it is in longitudinal waves, a bit trickier to see there, very similar to your amplitude, so the distance between your compressions and extension zones. The crest of the wave, we talked about that, that is the top of the wave there, that's your crest of the wave. And trough of the wave is the part down the bottom here, that is the trough. Okay, the dip, how deep it goes is your trough. Alright. Frequency and volume. These are other things that we need to know about waves and how they come about. If you've heard of FM radio, that's to do with the frequency modulation. That's how fast the wave peaks or the crests arrive. So here's some different waves, and we look at them and we can see that in wave A over here we've got the crests here quite close together, and here the crests are quite far apart compared to wave A and wave C. So the frequency has changed. Here the wave C, the crests are arriving quite a far apart, and wave A they're quite close together. And that equates to the pitch of the noise. So wave A is a high pitched noise, it's your high squeaking, and wave, this is low, so that's your deeper voices or deeper sounds or lower sounds. So that's the frequency. Now if we change the amplitude of the wave, so how tall it is, how big it is this way, that affects the volume. So this is a high volume, a loud sound. This one here, just the smaller amplitude, that is your low or quieter sounds. So wave A is the same loudness as wave C, but a higher pitch or a squeakier sound. Wave B is a louder than wave A and louder than wave C. So looking at the shape of the wave tells us quite a bit. And that connects us to our ears, sound waves. These are simply pulses put into the air by whatever's making the sound. In this case it's my voice talking to you, or it could be the speaker in the radio here, or the speaker in your headphones that you're listening to, and that's putting a compression into the particles in the atmosphere, in the air, creating a wave of energy that travels to our ears. And we can look at it in this way as the wave going up and down, carrying the energy to the ears over here. And that's where we head for next. But that's all about waves. Hope it's been helpful, and we'll see you next time.